In this video, we are going to learn on the units of measurements. Okay, before we proceed with the units of measurement, we have to understand first the term given in this topic. Let's say we have here a chemistry. What does it mean by chemistry? Okay, chemistry is the study of matter and the changes it undergoes. What does it mean by matter? Matter is anything that occupies space and has mass. An example here we have solid, liquid, and gas. These are the common matter. And there are also substance. Okay, substance is a form of matter that has a definite composition and distinct properties. This can be a H2O molecule. Okay, it can also be a methane, CH4. And the changes happen in the reaction can be a physical changes or chemical changes. Okay, physical does not alter the composition or identity of a substance. Let's say you want to change the ice to a liquid water, okay, or liquid water to ice. It only happens on the physical aspect. For the chemicals aspect, it will alter the composition or identity of the substance involved. In this case, we can also have H2, hydrogen gas plus carbon dioxide gas. So you can get a methane, CH4 plus H2O. This can change the chemical properties of the initial reactants. Okay, there are also 7 basic dimensions that we have come across in our daily life, and these include length, and the name of the unit is meter, and the symbol is m. For the mass is kilogram, kg, and the time we measure in seconds, s, and the electrical current ampere is capital A, and the temperature Kelvin, capital K, and the amount of substance mole, and also the luminous intensity candela, CD. From those 7 basic dimensions, we can also derive other dimensions. Okay, that include area, volume, velocity or speed, force, density, and pressure. So this one is the formula for each of the dimension mentioned here, and the units. Okay, meter squared for area, meter cube for volume, meter per second for velocity, Newton for force, and the density is kilogram per meter cube, and pressure is in Pascal. So here we have prefixes used with standard international units, SI units. So why do we need to use prefix of the SI units? Okay, SI prefix are used to form decimal, multiples, and submultiples of SI units. So they should be used to avoid a very large or very small numerical values. Okay, so here we have tera, giga, mega, kilo, deci, centi, milli, micro, nano, pico, and each of the prefix have their own symbol here, and the meaning and the example here we have the actual, we call it as the numbers given for the prefix. So for example here, tera, we have 1 times 10 to the power of 12 meter. So picometer is the a small one, 1 times 10 to the power of minus 12 meter. So next we have to convert the SI units. Okay, for the conversion of SI units, we can see here 1 cm cube equal to 1 times 10 to the power of minus 2 meter in bracket cube equal to 1 times 10 to the power of minus 6 meter cube. So here we have C, centi. Centi is we already know that is 1 times 10 to the power of minus 2. So we just need to substitute the C with this value. So and then we put it in bracket, and then 3 times 2, it will equal to 6 here. And next we have 1 dm cube equal to 1 times in the bracket 10 to the power of minus 1 meter times 3 to the power of 3 equal to 1 times 10 to the power of minus 3 meter cube. So here deci is 10 to the power of minus 1. So you just need to substitute in the unit. So you can 3 times minus 1, you will get minus 3. The same goes for, okay, this one is 1 liter equal to 1000 ml, also equal to 1000 cm cubed, also equal to 1 dm cubed. And in short, 1 ml equal to 1 cm cubed. And don't forget also 1 kilogram equal to 1000 gram, or in short, 1 times 10 to the power of 3 gram. So example here, what is the mass in grams of a 9.00 cm cube of zinc? Given here, the density of zinc is 7.29 kilogram per dm cube. So what we need to do first is we extract the information. Okay, volume of zinc given here 9 cm cube, and the density also given here 7.29 kilogram per dm cube. So what we need to do is we have to know the formula. Formula for density is equal to mass over volume. So the question asks you to find the mass in grams. So we need to find the mass. Mass is equal to, when the volume is bring here, density will times volume. So this is the formula that we are going to use later on. So what's next? So calculation here, we have to convert first. Okay, 9 cm cube to dm cube. So what's the value of the conversion after the conversion? Okay, here we know that 1000 cm cube equal to 1 dm cube. So x, you just need to cross this value, you times, okay, and then 1000 times x, 9 times 1. So you will have to rearrange back here. X equal to 9 times 1 over 1000. So you just cancel out the units, cm cube here. So you will get 9 over 1000. You will get 0.009 dm cube. That is the value for x. Then x here means that the volume. Okay, so you can use this formula. Okay, mass equal to a volume times density. Okay, so you will get and don't forget, you also need to convert kilogram here by times with the 1000 gram over 1 kilogram. So you will get the answer here is 65.61 gram. Okay, the temperature scales, there are terms that we need to understand in this topic. So the first one is the Celsius. What does it mean by Celsius? Celsius is a measurement of temperature in which 0 degrees is the freezing point of water and 100 degrees is the water's boiling point at the standard atmosphere. So here we have 180 mm pressure. And the Fahrenheit, degree Fahrenheit, is the temperature at which the pure water freezes at 32 degrees Fahrenheit, and the boiling point of water is 212 degrees Fahrenheit at the standard atmosphere. While the Kelvin is the unit used for the absolute thermodynamic temperature scale, that is begins at absolute 0 and only has positive values. And the formula that we need to calculate or to convert Kelvin to degree C is by using this formula, and to convert to degree Fahrenheit by using this formula, and to convert the temperature to degree C, so here we have the formula. So here we have the example on how to convert the temperature scales. Okay, the question given here, helium has the lowest boiling point of all the elements at minus 452 degrees Fahrenheit, and convert this temperature to degrees Celsius. So what do we need to do first is we extract the information. So the temperature given is minus 452 degrees Fahrenheit, and the formula that we need to use is that degree C equal to, in bracket, a degree Fahrenheit minus 32 degree Fahrenheit times 5 degree C over 9 degree Fahrenheit. So the calculation here, we need to substitute the value here. So we substitute the degree Fahrenheit with a minus 452 degree Fahrenheit, and you calculate, then you will get the final answer is minus 269 degree C. Scientific notation. So why do we need to learn about scientific notation? Because scientific notation is a way of expressing numbers that are too big or too small to be conveniently written in decimal form. So let's say here the number of atoms in 12 grams of carbon, we have 602 to 0000 and 0 and so on. So what do we need to do is we expressing this big number into a small numbers, okay, small notation, okay, like 6.022 times 10 to the power of 23. So this one we call it as scientific notation. So and in general, the formula will be like n, capital N, times 10 to the power of a small n, okay. So and the capital N is a number between 1 and 10, while the small n is a positive or negative integer. Okay, now let's take a look at the example on how to write the correct scientific notation. Here we have addition or subtraction. So the value given here is 7.4 times 10 to the power of 3 plus 2.1 times 10 to the power of 3. So here we have the same power, 10 to the power of 3, so we can add the two values. So we can get the answer as 9.5 times 10 to the power of 3. So how about we have a different value here? 4.31 times 10 to the power of 4 plus 3.9 times 10 to the power of 3. So we have a different power here, 10 to the power of 4 and 10 to the power of 3. So what we need to do first is we have to convert this value into to this. So we can get the 0.39 times 10 to the power of 4. So we have the same power here. So only then we can add these two values. So we can get the answer as 4.70 times 10 to the power of 4. How about multiplication? So here we have the value 8.0 times 10 to the power of 4 times 5.0 times 10 to the power of 2. So we can times these two values, but for the power we can add, okay, 4 plus 2. So the answer will be 40 times 10 to the power of 6, but we need to change this into a scientific notation where we move a 1 decimal point to the left, so we can get the final answer as 4.0 times 10 to the power of 7. How about division? Division is also the same like multiplication. In this case, we have the value 6.9 times 10 to the power of 7 divided by 3.0 times 10 to the power of minus 5. So the value at the front here we can divide, and the power we can minus, okay, minus. So we can get the answer as 2.3 times 10 to the power of 12. Significant figures. Significant figures are the digits of a number that are meaningful in terms of accuracy or precision. So we have to obey the rules how to write the significant figures. Okay, the first one here we have all non-zero numbers are always significant. Example given here is 3.456. So we have 1, 2, 3, 4. We have 4 significant figures. Second one is 1, 2, 3, 4, 5, 6, 6 significant figures, and the last one here 3 significant figures. And all zeros in between non-zero numbers are significant. So the zeros between the non-zero number here, 0 at the middle, we also consider that as significant figures. So in this case we have 4 significant figures, we have 6 and we have 5 significant figures. And how about zeros to the left of the first non-zero digits which are not significant? Okay, when you have 0 on your left hand side here, it is not considered as significant figures. So here we have only 2 significant figures, we only have 1, and this one we only have 3. Okay, if the last one, if a number is greater than 1, then all zeros to the right of the decimal points are significant. So when you have 0 on your right hand side, it is also considered as significant figures. So here we have 3. Here we have 3. We did not consider at the front here. We did not consider 0 at the front. So we have 1, 2, 3, 4, 5 significant figures. Here we have the example on how to write or find the correct significant figures when we have addition or subtraction. The rules here is that the number of significant figures in the result is set by the original number that has the smallest number of decimal points. So we have the key points here is the smallest number of decimal points. Example given here is 89.332 plus 1.1 equal to 90.432. So here we have 1 decimal points. So here we have 3 decimal points. Comparing both of the values, of course we take 1.1 as the 1 decimal point to write the final answer by round off to 90.4. The same goes to subtraction when we have the value given here 3.70 minus 2.9133 equal to 0.7867. So here we have 2 decimal points, here we have 4 decimal points. So we take the smallest decimal points to round off the results to 0.79. Example for multiplication or division having a different rule, and that is the number of significant figures in the results is set by the original number that has the smallest number of significant figures. So here we have the key points. Here is the smallest number of significant figures. Example given here is 4.51 times 3.6666 equal to 16.536366. So here we have 3 significant figures. So here we have 5 significant figures. So we have to take the smallest number of significant figures and we round off the final answer to 3 significant figures and get the answer as 16.5. How about a division? Here we have 6.8 divided by 112.04 equal to 0.0606926. So here we have 2 significant figures. So here we have 5 significant figures. So we have to take the smallest number of significant figures and round off to 2 significant figures and get the answer as 0.061.